So we have seen that relative motion using rotating axis is mainly used when we have two bodies with a body able to move on the second rigid body, okay? Or when we want to find the relative motion between two moving bodies, okay? Just 1 second, one student is not able to answer. Let me see what is the problem. Amanda, I don't have any message from you here to accept you. So try to do it again. I'm sorry, but one student is not able to enter the meeting. 1 second. Okay, so let us continue until. Okay, so we have in such frame, okay, we have developed last time that the velocity VB is equal to VA plus omega vectorial AB plus velocity of B relative to A. Okay, this term from this one represents physically, okay, the velocity of the coincident point. So I will repeat, I will give an example again. Imagine that you have, for example, this rigid body, okay? You have a rigid body doing a general plane motion. It's rotating and translating at the same time, okay? And you have an occupant or a person that is on the body, and this person wants to move on the body. So I have a person here, and this person is moving on the body, okay? Now, if I want to find the velocity of this person in the absolute frame, I can say that the velocity of this person in the absolute frame is equal to the velocity of the point on which this person stands now. So because this person is on the rigid body, okay? So because it's standing on this point will give its velocity to it. And this velocity is calculated by VA plus omega vectorial or B relative to A. It will give you the velocity of the point of the rigid body, okay? But since you have that the occupant is also able to move, it's able to move on the rigid body, okay? So in addition to the velocity given by the rigid body, I should add the velocity of the occupant with respect to the rigid body. So I should add velocity of B relative to A, okay? This will give me the total velocity of the occupant, which is the velocity given by the rigid body plus the relative velocity of the occupant with respect to the rigid body, okay? Now, for acceleration, it's the same concept. I derive this relation, okay? If I derive this relation with respect to time, I can obtain the absolute acceleration of B with respect to a fixed frame, where B represents the occupant, okay? B is the occupant, and A is a fixed point to the rigid body, okay? A is any point on the rigid body. On A, I am putting the rotating axis, small y, small z, and this axis will rotate with the body. So this is small x, this is small y. They are rotating with the body, okay? Now, I can measure the velocity of B relative to this rotating body. This represents VB relative to A. And if I want to measure the velocity of B relative to the fixed frame, then I should do this formula. I should do VB absolute is the velocity given by the rigid body to B plus the relative velocity of B with respect to the rotating body, okay? Now, to get a relation between accelerations, I will derive this relation. I derive this relation with respect to time. I get a relation between acceleration. So now to get the acceleration relation, okay, I will derive, as we said, we derive the velocity relation. The derivative is very complex. I will not go through details of derivation. If you are interested in the details of derivation, you can go to the course material, and I can explain it to you if you want, but not in class because it's very complex and it will confuse you. Okay, so for the students interested in derivation, they can ask me for it later, and I can give them the demonstration, or they can read it in the book. So once you derive, you are deriving the velocity expression. You will end up, why it's complex here? Because we said when we derive a vector, okay, we should pay attention if the unit vector are changing. And we said that RB relative to A is expressed in small I, small j. Okay, and small I, small j are rotating. Because they are rotating, as we have seen in last session, when I derive this vector, I should derive the unit vectors also. So it will give me new terms. And it's similar for velocity. When I derive VB relative to A, also VB relative to A is expressed in the rotating frame. So when I derive this term, also I will obtain several terms because I have dI by dt and dj by dt. And if I add all terms together, this is the final result I obtain. Okay? The final result is that absolute acceleration of B is equal to the absolute acceleration of A plus omega dot is alpha. It's like alpha. Okay? So it's very similar to the relation we have seen before, plus alpha vectorial AB. Okay? So let me help you here. You can, for these terms, you are familiar with them. This is alpha vectorial AB, and this term, okay, if you do the expansion, it will give you minus omega square AB. Okay, so this term also, and of course omega and AB are vectors. Okay, so this term, this one, is the same one we have seen before. It will give you the acceleration of the point on the rigid body. So it's AA plus alpha vectorial AB minus omega square AB. Okay, now what is new now? We have two new terms here. These are the new terms. The new terms are due to the relative motion of B relative to the rotating frame. Okay, this term, this one, is the effect of rotation of the body and relative velocity of the object. This term is called Coriolis acceleration. 2 omega vectorial relative velocity of B relative to A. This is called Coriolis acceleration, okay? Plus AB relative to A, which represents the relative acceleration of B measured by A in the frame, in the rotating frame XYZ, okay? So for the acceleration, if you want, it's combination of the acceleration of the point on the rigid body, which is given by AA plus alpha vectorial AB minus omega square AB, in addition to the relative motion, which will give you the relative acceleration and the Coriolis acceleration. Okay? Now, to understand better how you apply these formulas, we will do an example. Any question until here? I know it's a little bit complex, but once we do problem, I think you will understand. Okay, let's consider the following example. We have, at the instant theta is equal to 60 degrees, the rod has an angular velocity of 3 radians per second and an angular acceleration of 2 radians per second squared. At the same instant, the color C is traveling outward along the rod such that when x equals to 2 meters, the velocity is 2 meters per second and the acceleration is 3 meters per second squared, both measured relative to the rod. Determine the Coriolis acceleration and the velocity and the acceleration of the color at this instant. So what do we have here? Here we have a color. This is the color C, okay? Color C is moving on a rod. it's able to translate on a rod, and this rod is doing rotation. So what we can see here is that we have a rigid body, which is the rod. Okay, I have, this is the rod. Okay, this is the rod here. This is my rod. Okay, for my rod, it's a rigid body in rotation. Okay, on this body now, on this body, I have a particle able to move, and this particle is able to do what on the bar? C is relative to the bar. C is doing what?
Translation.
Translation. Yes, very good. It's doing translation. Okay, so I can say that the relative motion of the color with respect to the rod is a translation. Okay, and the velocity v, this velocity 2 meters per second, which represent which term? It represents the relative velocity of c with respect to the rod. So this is called v relative. Okay, it's measured in which frame? In the frame of the rod, which is the rotating frame, small x, small y. Okay, now 3 meters per second square represent what?
Acceleration of the rod.
Relative acceleration. Relative acceleration with respect to the rotating frame. Very good. Now, the question here is to determine the Coriolis acceleration, okay, and to find the velocity and acceleration of the color. When they just say velocity and acceleration, it means that they want the absolute value of velocity and acceleration measured with respect to the fixed frame, big X, big Y. Okay? So first, as we said, the Coriolis acceleration is given by which term? It's 2 omega vectorial v relative. Okay? 2 omega vectorial v relative will give us the Coriolis acceleration. Now, how to find the velocity and acceleration of the color? We will apply the general formula. Okay? We will apply it between which points here? Look at your figure. Between which points we will apply the formula? We will relate between velocity. Yes, velocity of c to which point?
O.
O, to O. So we will apply the relation between point C, which is moving on the rigid body, and with O, which is the origin of the frame. Why we considered O the origin? Because we know everything about O. O is a fixed point, so its velocity is 0 and its acceleration is 0. Okay? So now we will apply the kinematics equation. Vc equals Vo plus omega vectorial OC plus V relative, and AC is equal to AO plus alpha vectorial OC minus omega square. So this term is always in 2D, minus omega square OC. Okay? Plus, this is the Coriolis acceleration, 2 omega vectorial V relative plus A relative. Okay? So now, if we apply these relations, we should set the moving frame and the fixed frame. Okay? Now, please pay attention for one thing. You can always choose to work in the moving frame or in the fixed frame. So you can choose to express all your vectors or in terms of small I, small j, small k, or in terms of big I, big J, big K. But don't mix both, okay? So, or I express all my vectors in terms of small I, small j, small k, or I express all my vectors in terms of big I, big J, big K. I will choose what is easier. In this problem, for example, it's easier to work in terms of small I, small j, small k. You know why? Because if you go back to the figure, okay? If you go back to the figure, the relative velocity is along the small I, and the relative acceleration is along the small I, okay? So instead of, if I want to work in big I, big J, I should decompose the velocity into two components. I do, for example, for V, It's 2 cosine 60 big I minus 2 sine 60 big J. While if I work in small I, small j, small k frame, I have only 2 times small I. So it's easier to work in small I, small j, small k. Therefore, in this frame, the relative velocity is plus 2I. The relative acceleration is plus 3I. Vector OC is along small I. It's plus 0.2 small I. Okay? And of course, alpha and omega will be along which axis? Alpha and omega are along which axis?
The K. Alpha.
K. And K is common for both, okay? It's common for, K is the same for big I, big J, big K, and small I, small j, small k. It's the same one. It's perpendicular to the screen, okay? And here, I have that omega and alpha are in which direction? In the clockwise direction. So if I do the right-hand rule, they are along minus k. So I have omega equal to minus 3k and alpha equals to minus 2k. Okay? Now I can apply my relations. I go back to my vectorial relations. After I found the expression of all my vectors, okay? And since O is fixed, so VO is 0 and AO is 0. Now if I replace in my equations, I can find the velocity of C. So VC is 0 plus omega vectorial OC, which is minus 3k vectorial 0.2 small I, plus 2 small I, which is the relative velocity. Now, if I do expansion here, k vectorial I will give me plus j, and already I have minus, so it's minus 0.6j plus 2i. Now, if you want, at the end, if you want to express your vector function of big I, big J, or all you have to do is to project small I, small j on big I, big J. So as simple as that, you can convert from one frame to the other in a very simple way, okay? And now for the acceleration, I apply the relation AC is equal to AO plus alpha vectorial OC minus, if you want, in general, this term is easier to calculate by minus omega square OC instead of doing these steps. Instead of doing omega vectorial OC and then do omega vectorial the result, it's easier to do minus omega square OC. It will give you the same value, okay? Plus 2 omega vectorial V relative plus A relative. So now if I apply this relation and I do the expansion, I obtain as a final result 1.2 small I minus 12.4 small j. Okay? Now, how to project small I, small j on big I, big J? Let's go back here to the figure. Okay? If you look at this figure, this is small I. This is small I, okay? If I want to decompose a small I into big I and big J, what should I do? Who can tell me? So small I is equal to what? Project on big I, what do you have?
Cosine 60.
Yes, cosine 60 times big I, okay? And along big J?
Sine 60.
But
J.
minus, okay?
Minus, yes.
Minus sine 60 j, okay? And now for small j, what do we have? This is small j, okay? This is vector small j. If this angle is 60, then this one will be 30, okay? So for small j, it is or cosine 30 or sine 60. So it's sine 60 big I, and along j it's a positive projection, so plus cosine 60 big J. Okay, so I can transfer easily from one frame to the other by replacing small I by this expression and small j by this one. And if they don't force you to work in a certain frame, you can work in the frame you want. Here it's easier to work in small I, small j. Okay? Any question on this problem? So let us move to another one. Do you remember this problem? We have done this problem in which chapter? If you remember, we did it in
12.
chapter 12.
12.9.
In chapter 12, we did it. What was the question? Find velocity of, and acceleration of B relative to A. And if you remember, I told you we cannot do in this chapter the acceleration of A relative to B. Why? Because we said that B is doing rotation. Because B is doing rotation, the axis of B, the frame at B will do rotation with the body. Okay? And we said that in this case we cannot use the formulas of chapter 12. If you remember, what was the formula of chapter 12? The formula of chapter 12 was V, for example,
is VA plus VB relative to A.
yes, we can calculate VB relative to A by saying that VB is equal to VA plus
VB relative.
VB relative to A. Okay? And this directly will give us the relative velocity. But I told you then you cannot calculate A relative to B. Why? Due to rotation of the frame of B. Because the rotation of frame of B will give us vectors that are changing in direction. So when we do the derivative, we will obtain additional term. What is the additional term? It's the one we have seen in this chapter. In this chapter, we have seen that if we put a rotating frame at B and we want to calculate VA, then VA will be equal to what? It will be equal to VB plus what? What is the new term to add? Plus omega factorial BA, okay, plus velocity of A relative to B. Okay, so what is new here? Which term is new? This one. This term here is due to what? This term is due to the rotation of B. Okay, so whenever I have a frame, the frame attached to B is doing rotation. When I have a frame doing rotation and I want to measure the velocity of any body relative to this frame, I will use this relation. Okay, I cannot use this one because this one is only valid if the frame is translating, which is the case for plane A, but not the case for plane B. When I want to measure A relative to B, which is rotating, I should use this formula for general relative velocity for rotating axis. Okay? So now, to find the velocity of A relative to B, all I have to say is VA equals VB plus omega vectorial BA plus the relative velocity. This is what I want to find. I want to find, this is the question. I want to find this component. This one, VA relative to B, okay? So I know the absolute velocity of A, I know the absolute velocity of B. Now how to find, because what is absolute velocity of A? It's given. It's plus 700 km per hour. And the absolute velocity of B is given also, it's plus 600 km per hour. So I still need to find omega. Who can tell me what is omega of the rotating frame? What is omega of the rotating frame? It's equal to the rotation of the rigid body, which is the plane B. Okay? Because the frame is attached to plane B, so it's rotating with it. How to find omega of the airplane?
نجيب V square over R نجيب ال V
V
جي
square
بالار
over
لما
R لا V square over R
لا
هي
لما
normal acceleration. أنا بدل أوميجا. كيف بجيب الأوميجا؟
في على ار.
برافو. أوكي. تجيب الأوميجا هي V على R. Okay, because in rotation, what do I have? In rotation, I have V linear equal to omega times radius. Okay, the radius is given, it's 400 kilometers, and the velocity is given, it's 600 kilometers per hour. So I can calculate omega by 600 over 400. Okay, very good. Now I can do my calculation. But before moving to my calculation, now if I want to apply the acceleration relation, for the acceleration relation I need alpha of the rigid body. How to calculate alpha? غادي لا V equal omega R لأنه you have rotation. Okay, plane B is doing the rotation on a circle, and they told you that this rotation has a radius of 400 kilometers. So the linear velocity, if in case of a circle, the linear velocity is the angular velocity times the radius. Okay.
هالديريفيتيف تبع S is equal to R فتة صح؟
صح.
Okay.
Now how to find alpha? How to find alpha of rotation? Who can tell me? What is the angular acceleration of rotation?
الفا كروس ار ماينس بلس في اوميجا سكوير ار يمكن او شيء.
الفا
معنى الاوميجا
مش الاكسلريشن. الفا
الالفا هيدي اوميجا
AN هي اوميجا سكوير ار. AN هي في سكوير اوفر ار. بس AT شو هي AT؟ A tangential. كيف بنجيب؟ مش A tangential هي dV by dt. اوكي. هي equal to what؟
الفا كروس ار.
Alpha times R. Okay, alpha times R. So to find alpha, I do the tangential acceleration over R. What is the tangential acceleration of plane B? Look at the figure. This is A tangential. A tangential equal 100 kilometer per hour square. You know from the unit that this is the tangential acceleration. And it's in the same direction of velocity. And how to calculate the normal acceleration? The normal acceleration here is what? Is V square على R. Okay? So now we know everything. We know the acceleration of B total. Acceleration of B total equal tangential acceleration plus normal acceleration. And alpha is equal to the tangential acceleration over R. Okay? Now we move to apply our relations. So we have first, for velocity, we will use the relation VA equals VB plus omega vectorial BA plus the relative velocity of A relative to B in the rotating frame. Okay? And AA is equal to AB plus alpha vectorial BA minus omega square BA plus 2 omega vectorial V relative. This is the Coriolis acceleration plus A relative. What we want to calculate in our problem is these two. We want to calculate relative velocity of A with respect to B. So it's the velocity measured by the pilot of B. And this is the relative acceleration. These are the terms we want to calculate. We know everything else. Okay? So now, in order to replace in my formulas, as we said together, we should calculate AB normal, which VB square over rho, and AB absolute is the summation of AB normal plus AB tangential. So we can calculate it. It will be 900I minus 100J. And as we said, omega is VB over R, and alpha is AB tangential over R. So we can calculate all the variables needed for our equations. Now we replace back. When we replace back in the equation of velocity, okay, I have VA is 700J. This is the absolute velocity of A measured with respect to the fixed frame. Now VB is the absolute velocity of B measured with respect to the Earth, and they are given 700 and 600. They are given in the figure. Now alpha, I calculated alpha. It's minus 1.5 K. Now look for the sign. How do I know if it's minus or plus? Who can tell me? I go from the right hand rule. I go back to the figure here. Okay, look, your airplane, the velocity is upward. So if you do the right hand rule, you will see that omega will be in the clockwise direction. Okay, if you do your right hand rule, it will give you that it's rotating in this direction, in the clockwise. Because it's in the clockwise direction, so it's along minus K. Okay, because if you do the right hand rule, your first finger, the finger of your hand will be towards the screen. So it's minus K. However, for the tangential acceleration, because the tangential acceleration is opposite to the velocity, then if I do the right hand rule to find alpha, alpha will be opposite to omega. It will be in the counterclockwise direction. So it will be along positive K. Okay? So here alpha is along positive K and omega is along negative K. Okay? Now if I go back to the calculation, okay? So we replaced alpha by, omega by minus 1.5 K. Vectorial vector BA, okay, is minus 4I because it's along the horizontal and directed towards the left, plus the relative velocity. The only unknown in this equation is the relative velocity of A measured by B, so we can find it. Okay, this is the calculation will give us this relative velocity, and you will conclude that VA relative to B is different than VB relative to A. Okay, because VB relative to A was what? Was 100 only. Okay, because it was equal to
and with respect to translating
yes,
axis.
because it's with respect to a translation, it was VB minus VA. It was equal to minus 100. Okay, while here it's plus 94. You don't have the same magnitude because B is rotating while A is translating. Okay. Now, if we do it for acceleration, if we apply the relation for acceleration, so absolute acceleration of A equals to absolute acceleration of B plus alpha vectorial RA relative to B, which is vector BA. Now this term, okay, you can replace it by omega square BA, okay, plus 2 omega vectorial V relative plus A relative, okay. So now we replace AA is given, it's 50J, AB is decomposed into tangential and normal, and we have seen that it's equal to 900I minus 100J, and alpha is along positive K. This is why we have considered plus 0.25 K. Vectorial vector BA, which is minus 4I. Okay. Now they did the long method. They replaced omega and BA by their values. You obtain this. Okay. And this is the relative velocity we have calculated in the previous step. So we replace VA relative to B by 94J. And the only unknown is acceleration of A relative to B. Okay, so this is my only unknown. So I do the expansion, and after doing the expansion, I take I terms together, J terms together. I get A of A relative to B. And of course, it will be different in magnitude than A of B relative to A. Okay, any question on this? So we are done with chapter 16. Okay, if you want, we can do next session review for the exam, or we start a new chapter, so as you like.
On Thursday, can you tell us more what will happen?
On Thursday, after the session, we will do a small test. It's not graded, it's just to do a small prova of the exam. I will monitor you on Zoom because we will do this in the exam. So we will do a small trial and you will see the type of questions.
نحن we open Zoom on our telephone and we use our computer to solve ولا كيف؟
No, you open Zoom on your computer. And at the same time, you open Blackboard and you